Who here is a Bayesian? Who wants to be a Bayesian? Yeah, everyone wants to be one. All right, so with that, almost no introductions. Everyone, please welcome Andrew Gelman.
Thank you. Nice to meet you all. I think today I'll tell you some stories that, and I'm hoping that you'll be able to make use of them in your own work. So I'll try to figure out how to make that connection, because as the story, well. There's a saying that theoretical statistics is the theory of applied statistics. And what we do is the most important thing in understanding what we do, which means we need to reflect upon what we do. So when I'm speaking, I want you to think about your own work and how these ideas are relevant or perhaps not. So let me... Okay, I'm going to start with a story from a couple of years ago, which was estimating the number of people that had coronavirus. And a study was done by some Stanford professors of where they gave people COVID tests. I don't remember the details. It was the kind of COVID test that's supposed to say whether you have the antibodies. So it's supposed to say whether you had ever had it. And they surveyed 3,000 people in the county in California that contained Stanford University. And out of those, 1.5% had COVID. So you can kind of estimate that the COVID rate is about 1.5%, which was kind of, well, you can estimate that. That won't be quite right for a couple reasons. So the first thing is that the test have some false positives and false negatives. When something is a very low rate, a low prevalence in the population, then the false positive rate can be very important. So you need to adjust for that. The other problem was that the survey overrepresented people who lived near. They asked people where they lived, and they were all residents of the county, but it overrepresented people who lived near Stanford and underestimated people who lived further away. So they did some survey adjustment for that. The people who lived further away had a higher COVID rate. And so when you do this adjustment, you get a higher number. So when they did both adjustments, they got an estimate of about 3% instead of 1.5%. 3% was really big. It was higher than people thought, so the study got a lot of headlines. Some colleagues and I looked into this, and it turned out that it turned out that it helped to use a Bayesian approach, as Jared would say, I guess. And in particular, we needed to account for uncertainty in the false positive rate. And that was driving a lot of, when you account for the uncertainty in the false positive rate, you end up with an interval for the rate of people who had ever had COVID that went pretty much all the way down to 0. Now, I don't think that 0 people had it, but I think that there was a lot of uncertainty. Even a sample of 3,000 people isn't really enough if you're trying to estimate something that has a prevalence of 1% when the false positive rate is in the order of 1%. So we reported that there was more uncertainty, which was fine. Going forward, people wanted to use this method for other problems. So I was working with some colleagues in Australia who were doing pretty much using the exact same model, but this time they were trying to do a better job of post-stratifying and adjusting for differences between the sample and the population. So they started with a prevalence, and I believe it was similar. It was around, well, let's just say after adjusting for the false positive rate, the estimated COVID rate was around 1%. And then the sample size was larger. There was enough data that they could be pretty sure it was positive. As we post-stratified on more variables, so you can post-stratify on age and sex and personal characteristics and also geographic characteristics where people live. As as they post-stratified more and more, their estimates, the estimated COVID rate kept, I don't remember which way it goes, but it doesn't really matter for this story, okay? So I'll say it kept going up. And so it kept going up, like it was like 1% and 1.5%, and like not huge. Like any of these numbers were kind of plausible, but it was drifting upward. Now, that's not like a surprise in the sense that, or maybe it was going down, but again, that doesn't really matter. So it's not problematic that when you do more adjustment, the estimate changes more. Like that's the whole point of doing adjustment, is that it might change. But it was kind of weird because we then did the multi-level regression post-stratification analysis, post-stratifying not on the population numbers, but on the sample numbers. So you can do that. You can do MRP to a survey, like to itself, and post-stratify in itself. It still gives you more stable estimates and more stable small area estimates. But it also gives you a population estimate. If it were causal inference, I would say it's the sample average treatment effect instead of the population average treatment effect. But in sampling, it's just the sample estimate versus population estimate. Anyway, we went back, and as we went forward, adjusting for more and more things, the sample estimate kept drifting too. And it just didn't seem right. Like it's, again, not that it's impossible, but we looked more, so we looked and we saw that as we were adjusting for more, our estimated false positive rate was going down. And when the false positive rate goes down, it attributes more to real cases. And I think there was something weird. We're still kind of in the middle of this because these are very busy people. But I think that the next step was to simulate fake data from a world in which the model was true and see if this would happen. When we simulated fake data from a world in which the model was true, this didn't happen. Like, we didn't have this problem. But we're having it in our problem. Then we thought maybe we should simulate from the prior. And when you simulate from the prior, it's kind of, we use kind of weak priors. When you simulate from the prior, you get really weird results because like a lot depends on how low the false positive rate is. So that makes me think maybe it's a problem with our prior. I kind of want to stop here and just say, like, as a story, that's kind of something that happened. Okay, that's one story. Now I'll tell you another story now. I was working with a student of mine who was who had a physics background. And so I was talking with him because there was an example that I would always give when teaching. And I gave, it was kind of a fake history of least squares. It was a way to help students understand least squares based on understanding math. So I told the students how, you know how 2 points determine a line, right? 3 points determine a plane. So it's also true that 5 points determine an ellipse. So if you have 5 points, I think this is right, that an ellipse has 5 parameters. So if you have 5 points from an ellipse, you can draw the ellipse that goes through it. So then I said, imagine your Gauss or Laplace back in the dawn of quantitative science, and they're plotting the motion of planets. If you have a planet has an elliptical orbit, approximately. If you have 5 measurements of the planet, you can draw a curve through it, and that's the ellipse. What if you have 6 measurements? What do? Like, you could pick the first 5, the second 5. You could pick various sets of 5. What if you had like 30 points and you wanted to draw an ellipse through them? You could pick the, I guess I have to do it here so you can see it. You could pick these 5 or these 5 or these 5. So you could imagine a statistical method where you pick all the sets of 5 and draw all the curves, and then you kind of average them. Well, like, so that kind of gets you to least squares, right? In fact, actual linear least squares, it's not well-known fact that with regular old linear regression with one predictor, you can actually get the least squares regression line by taking all pairs of points and connecting them with lines and averaging all those slopes. But it's a weighted average where you weight the slope by the square of the x difference between the 2 points. Well, that kind of makes sense, like, if you think about it, because what if you have 2 points with the same x, then the slope's infinity, but it gets weighted by 0 squared, so that gets knocked out, so it doesn't matter. Anyway, it's a kind of fun formula, a fun intuition. But then you can continue and say, what if you have a planet and it's going like this, and then like a Death Star comes in from hyperspace, and then the planet, it starts going like that. Like it's okay. What happens if you try to fit, like, well, you could fit an ellipse to these points or these points, or you could fit to these, so that it would be hard to get from one to the other there. It would be hard to get a solution. That's an illustration of the Folk theorem, of the Folk theorem of computational statistics, which is that when you have a problem with your computation, you often have a problem with your model. So in this case, there's a kind of two stories, and neither one fits all the data. So in some sense, you don't want the solution. OK, with those as our starting points, I want to talk now about metaphors of statistics or data science. I think we can't say statistics anymore, so I'll always say statistics or data science. That's fine. Like, words change. I don't mind that at all. Like, it's like that's the way it goes. You know, that's completely reasonable. So I have two metaphors for statistics or data science. I think they're both valuable metaphors, and we use them in different ways. One of them is statistical practice as engineering, and the other is statistical practice as science. So statistical practice as engineering, it's like you think of like building a bridge, or maybe like you're designing a product, right? So you think about how it's going to be used, and you want it to work in a bunch of settings. Like, how do we build a bridge? I'll never build a bridge, but like, how would I build a software product? I would start with a simple example, a little model. I'd test it. Then I'd get it out there. Once it's out there, I'd have beta testers and so forth, and I'd have some sort of continuous quality improvement going on. Well, that's kind of how it works with our statistical methods, right? Like, we have ideas. They work on certain problems. Then we try them out. We put them in articles and books, and we have people like continuing to do it, continuing to do these things. And it's an engineering process. You're continually trying to improve it, and also continually trying to figure out what went wrong with it. The other metaphor is statistical practice as science. And I like to, so you could say that statistical practice as engineering is when you're developing a method. Statistical practice as science arises when you have like one data set or one problem coming up. So an example would be that, oh, I didn't finish, sorry. OK, hold those thoughts. OK, I didn't finish the planetary motion example. So I had this example, and when I would teach class, I would always do it on the board. I'd write it on the board. And then I thought, well, let me illustrate it like in Stan. Like, why not actually do it and see what happens if you put the Death Star in and try to fit the model and see how it doesn't work. So I started with the simple example. You have a sun and a planet. This planet's moving around the sun, and you have 30 measurements of the planet. It goes like from here, like I did like a little more than half of an orbit. And you throw Newton's equations into Stan and have it figure out the position of the star and the position of the planet at each time, the mass of the planet, you know, all the parameters. And so I simulated data, and then I asked the student to do it because he knew physics. So I figured, oh, because Stan has differential equations. So I don't want to put in that it's an ellipse, right? That's kind of cheating. I want to actually put in the differential equations of motion and then have it just do it. That's more pretty, right? So he did that, and he found something funny. He ran 8 chains, and like 5 of them did really well and found the parameters just fine, but 3 of them were really bad. And actually, it's one of these funny things where if you've simulated 4 chains, you could just get lucky and have all 4 be in the right place. But otherwise, like, you have problems. And if you look at the parameters when it was wrong, they were really, really wrong. They were terrible. That happens sometimes in computation, that the objective function is very flat. When you're far away, it's kind of hard to find things. So I said, well, in real life, you'd have a little bit of prior information on these parameters. So let's try it with a stronger prior. And it was still having this problem over and over again. So we had to look at it very carefully And we're simulating from the truth, right? They said, let's strip down the model. So we're going to say that the star, we know the position of the star, we know the initial position of the planet. Like we said, so we only had like 2 parameters left, or maybe even 1 left. And it was, I think then it worked, but then we added a couple parameters and we're still having this problem. And it was doing this. And then it turned out, well, it was kind of funny if you looked at the likelihood function, it was like, there was like a maximum likelihood solution and a range near it. They were all very reasonable for one of the parameters. Let's say it was like the mass of the planet. And then you go out, the likelihood goes down, and then it very slightly goes up, and then goes down, and very slightly goes up. Now, when I say very slightly goes up, I mean the value of the likelihood function was like 10 to the minus 10,000 times the, I mean, that's not 1/10,000th as high, 1/10 to the 10,000th as high. But like, no prior will get rid of that, really, because it really went down and then up. If you looked at the inference, the estimated parameter, like you want the planet to do this, and what it was doing was going around like 1.5 times, which was a real, and if you have it go 1.5 times, like the planet is very heavy, it gets sucked into the star, then you, like, it's a terrible fit, but it's a local maximum. And it's a terrible local maximum, but the things near it are even worse. You should really never be there. So you can actually solve this in different ways. If you have 8 chains and some of them don't work, then you have to throw away the bad ones, which is fine. Like, you can compute these, you can estimate the mass of these parts of the density and say it's so low that you don't need them. Or you can do leave one out, predictive model averaging, which is called stacking, and get rid of it. Or you can just use good starting points. So I learned something very important from this example, was that you either have to be using good starting points, or you have to be willing to throw away these chains, which all of which makes sense. There's no statistical reason why you can't pick your starting values for an algorithm. There's no statistical reason you can't throw away chains that are far away from where you want to be. But we had been in a kind of rut in which we were always like using default starting values, because like you're writing computer programs, you don't want to have to specify your starting value, but sometimes you do, right? So we kind of learned something. So I guess okay, so that's the end of that story. Now let me get back to what I was saying about the analogy. So statistical practice is engineering. Statistical practice is science. So I would say, like, when we're doing statistics, there are 3 tasks of statistics. There's estimation, exploration, and adjudication. By which I mean sometimes we're estimating parameters in a model. Sometimes we're fitting a model in order to explore data. And sometimes we're trying to adjudicate between different models. Now, in the COVID example I gave you, it was pretty much straight up estimation problem. But if you notice what I was doing when I talked to you about these examples, this is what I want to get at, okay? Is that I was acting like a scientist in the sense that I was standing outside my model and data and trying to figure out what was going on. And I feel like this is an aspect of statistics that's not in the books, and not even like in my own books. Like, and so let me ask you this. I want to reflect a moment on what is science, okay? So when I say science here, I mean like not like a null hypothesis, you know, like hypothesizing like my null hypothesis, not a statistical model. I mean, I want you to start with a hypothesis like salt helps beans grow faster. That is, I want you to put yourself in 4th grade, okay? You are now in 4th grade. You're this high, and you are learning about science. And what they tell you is about science, you start by forming a hypothesis, like salt helps beans grow faster. Then you design an experiment. I'm going to have these two pots of beans, and I am going to put the same amount of water in both. I'm going to put more salt in this, then more in that. Then I'm going to run the experiment. I'm going to gather data. Then I'm going to evaluate my hypothesis and modify my hypothesis, design new experiments. Like, what if I find nothing? Do I say the hypothesis was false? Does it mean that I need more data? Do I want to try different conditions? Maybe it depends on the temperature, so forth. That's kind of what we do. And I gave you a couple examples from my own work. I can give you more. I'm going to throw examples at you for a moment. Okay. I was contacted by someone from Wikipedia because they were doing some A/B tests. And they did a test where they were testing some silly little thing. They said, this is a silly little thing. And they said, rhetorically, why are we testing silly little things? Because it's free to test silly little things. People are on Wikipedia anyway. They have the screen that goes up saying, would you like to pay $3 to help Wikipedia do good stuff? And once it's there, they can put the screen in, they can do it in different colors, they can do different things. They're doing it anyway, they might as well experiment. So they experiment all sorts of silly things, and they tried a silly thing, and they found a very large effect, an implausibly large effect. Why was that? What's going on? Was it they're doing multiple comparisons? They've just looked at too many things and they finally found this? Did they do the statistical model wrong? Is there a bug in their code? Well, it turned out, it turned out that they weren't actually something. It was a bug somewhere because they ran the experiment for 12 hours, and they had the data for how many people each hour got the treatment and the control. And for a couple hours, it was equal, and then after that, almost everyone was getting the treatment and nobody was getting the control. And it happened that the baseline level of country, the experiment was from 4 a.m. to 4 p.m. to 4 a.m., and in the middle of the night, people go on Wikipedia, but when they get that screen, they're less likely to give money for whatever reason, or those people are less likely to give money, right? The night owls. So because the treatment was assigned, more likely to be assigned at night, it looked like the treatment had a negative effect, but if you had adjusted for the time or just done the damn randomization correctly or not lost half your data or whatever, you would have got a reasonable result. Okay, that's a story. Another story is ethnicity. Okay, well, I'll tell you, a bunch of years ago, some psychologists did this experiment where they gave people a quiz. Each quiz gives you 4 cities, and they'll say, which is closer? Is New York closer to Boston or San Francisco closer to LA? Is Denver closer to Salt Lake City or Minneapolis closer to Detroit, et cetera? Lots of pairs of cities. Those are kind of tough ones, but they gave people some easy ones too. Lots of pairs of cities. Each time you have to answer the question. You answer enough of these, then you can use a statistical model to estimate your mental map of where the cities are. Well, they did it on a bunch of people, and then you get this mental map where, of course, cities in the West are kind of close to each other, and then cities in the East are really far apart because people have that mental map. I guess if you give the question to people who live in California, it might look different than if you give it to people who live in New York, so forth. They did a similar thing where they asked, well, they did a bunch of different things. They also asked the same thing with animals. So you could say which animals people think are more similar to other animals. Very interesting line of reasoning. I decided to do this with ethnicities and nationality. You ask people questions which is Irish and Italians, are they closer than Germans and French people, right? Well, Ireland is far from Italy, and Germany is close to France. Yet, Irish and Italians in America, there's some similarities somehow, culturally, whatever. So you have this whole story. We did this. We didn't do it. We're designing it. And the idea would be to get people's mental maps of nationalities and religions and cultures, and then you could ask questions like, do liberals have a different mental map than conservatives? It's just a different project. Something completely unrelated. A bunch of years ago, we published a paper called Enhancing Democracy Through Legislative Redistricting. Very clever, right? Gerrymandering is supposed to be bad, right? No, it's good for democracy. We're enhancing democracy through how could that be? Well, every 10 years they redraw the district lines, and there was a concern first that there would be partisan bias, that parties would redraw the districts to help them and hurt the other party. Second, that there'd be a lack of electoral responsiveness because they would draw the district lines to protect incumbents. So that was considered bad. We did an analysis based on state legislatures from the 1970s and 1980s. This was a long time ago that we published this. And we found that actually, after redistricting, there tended to be less partisan bias and more electoral responsiveness, more competitive districts than before redistricting, which seems odd, right? Well, the reason is that redistrictors are under a lot of constraints. So they are constrained to keep equal populations in the districts. Also, they were constrained in the sense that most states or many states had divided government, and so they had to compromise to pass a redistricting bill. And finally, the courts would throw out the most egregious gerrymanders, as the saying goes. So connecting this to what is science and all. So we have a bunch of hypotheses, like that you come in with some models of the world, like how redistrictors work. It's a mixture of what I call adjudication between different hypotheses and estimation, that we're trying to estimate the effects. We fit a model estimating the effect of redistricting, and then we found that there was an interaction. And I won't go into all the details except to say the interaction was very important. We had a lot of data issues, things happening in individual states that we had to kind of handle. I feel really bad about this project. It won an award. Like, we won an award for it from the American Political Science Association. We were like, this was influential work. And that's why I feel bad, because actually I don't think legislative redistricting enhances democracy now. I haven't studied it formally, but it looks like there are some states like Wisconsin where it's really anti-democratic, and conditions have changed. And we should have written a paper saying back in the 1970s and 1980s, redistricting enhanced democracy, but we don't know what happens in the future. So our paper had a big implicit model. And the big implicit model was what happened in the past is going to be descriptive of what happened in the future. But we usually care about the future. And that's fine, right? Like, I can't knock our paper for not being a crystal ball. But I can knock us for not at least speculating, like not saying, if we wanted to say, hey, we consider that the effects in the past will continue in the future because the effects in the past arose because of certain conditions, such as competitive states and blah, 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 and we expect that these conditions will continue. That's fine, but we didn't say that, right? We just, and I feel really bad. So, but what I really want to get at with those examples was how what we were doing was like fourth grade science. Like the Wikipedia thing, right? Like, what's happening? There's like this weird phenomenon. Let's try to understand why are we not? So they started with a certain hypothesis, but then once you get the data, you have this. So there's like two levels of science, right? So the first level of science is why you're doing your study in the first place. Like, I have a hypothesis about nationality and ethnicity. That's why I want to do this study about, right, the nationalities and the ethnicities, the mental map. I have some hypotheses. They're kind of vague, a little bit more vague than salt makes beans grow faster, but not that vague. Like, I mean, salt makes beans grow faster is a vague hypothesis too, right? Because it's got to depend on the conditions. But then when I start thinking about gathering data and we simulated some fake data, and we found it was actually harder to recover the positions of these groups than we thought it would be. Then we're doing this other kind of science, like this kind of detective work thing, where we start gathering data at that level. Okay? So when I say gather data, I kind of mean two things. One thing I mean is like gathering data. Like we have theories of redistricting, so we gather the data about competitive elections. But then the second thing is when we're in the middle of doing our statistics, then we start doing these, like, we have these little hypotheses. Like, wait, the model doesn't fit. Why not? Is it a bug in my code? Is it that actually my prior is too weak and I didn't really think about that because in the past I had analyzed data where I didn't need a strong prior? Is there a problem with the data that I hadn't seen? Like, and let me probe it. Let me do some experiments. Let me do some leave one out cross validation. Let me try things. Okay. What I would like you to do just for a minute, okay, or 2 minutes, is to talk with your neighbor about a project that one of you has worked on. And I just want you to frame it as a 4th grade science project. And like consider like what you were doing in your data analysis or whatever, where you were like being a little scientist. So could you do that for me for a minute, please? So here, you can talk with that gentleman there. Hey, you can talk with... Okay. So, yeah. So this is kind of important. In fact, like often, like at the end of my talk, I like to say, like, what can you take home from this talk? That's what you can take home from this talk is to reflect on what you're doing and think of it. Now, this is so this is not like, it's not in our books that we do this, right? So what is this not? Well, it's not a pre-registered study. It's not that you fit, like think of paradigms for statistics. So one is the pre-registered study, and you have the statistical properties of your method. Another paradigm of statistics is the kind of BDA paradigm that you're going to fit a big model. And you might have to work at it and build up, but eventually you have this big model and it's just sitting there, right? But that's not what you're doing either exactly. And another paradigm, which is from econometrics, is that you're doing inference for something called theta. And that's like what you care about. Now, it's not that, but yet I'm not saying that you should forget all of what you've learned about statistics. So here's a bunch of key issues in statistics that come up. Okay, data quality and measurement, bias, variance, partial pooling, extrapolation, generalization, causal identification, and mathematical modeling. Now, these are all important issues. Like they come up, for example, in our Enhancing Democracy Through Legislative Redistricting project. Obviously, there are issues of data quality. How do you even define a competitive district? And measurement, you have issues like uncontested elections, other things that you have to deal with. We have to think about mathematical modeling, like even things like using normal distributions, like are they appropriate, bivariate models, time series models. We care about causal identification. So to what extent can we think about redistricting as a treatment and so forth. So we think about all these things, but I feel like when I'm doing stuff, I'm actually like doing a lot of experimentation. And so like here's a kind of thing, I think these are the things I put in the abstract, but like what if we have some of our hypotheses are not scientific hypotheses. So it's not a hypothesis that redistricting is good for democracy or salt makes beans grow better or whatever. It's a hypothesis, an internal hypothesis, like n equals 200 will be enough for this study, right? Or a simple two-dimensional distance model, that will work. I don't need to go beyond 2 dimensions. I'm fitting a model, I'm doing A/B testing, and I think the treatment effect will vary over time. I think a simple random walk model will work with a normal prior on the jumps. Or like I have a research question. Yes, I think I can estimate it from the data. So these are hypotheses that are hypotheses about data quality, hypotheses about bias, hypotheses about extrapolation. I think for my hypothesis that I can just do inference for this sample and not worry about non-representativeness. In order to study a hypothesis like this, I'll do a little experiment. Like I might do typically these experiments are simulation studies, but sometimes you might actually go and gather a little bit of data or analyze existing data. You could do mathematical modeling, which is a kind of shortcut to simulation. The simplest example is a sample size calculation. So example I've talked about before was from nearly 20 years ago now. It was a study somebody did of beauty and sex ratio. And they found that beautiful parents were more likely to have girls. It was based on a survey of 3,000 people. And it was statistically significant. And it got some press, this result. We could do a little bit of, there's an implicit hypothesis in their study, not a hypothesis about biology, but a hypothesis about statistics. And that's the hypothesis that 3,000 people is enough people to estimate a difference between sex ratios of pretty and ugly parents. Well, we can do a little bit of statistics. Actually, this one I don't even need to do a simulation. I have n people, and half of them are beautiful and half of them are ugly. It's not quite right, but we're simplifying life. N over 2 of them have babies, n over 2 of these people have babies. I want to estimate the difference in the probability of a girl birth. So I get a difference and a standard error. The standard error is the square root of 0.5 squared over n over 2 plus 0.5 squared over n over 2, which is 1 over square root of n. So for example, if n were 100,000, then 1 over square root of n is 0.01, 1%. So you can, if you have 10,000 people in your study, that should allow you to estimate the difference in sex ratio, a difference of 1 percentage point. But actually, if you look at the literature, you never see differences. Like, a difference comparing beautiful people to ugly people, that would be much less than 1 percentage point. Like you can look at difference in sex ratios comparing old mothers to young mothers, black parents to white parents, rich to poor, all sorts of things, and you get differences that are a half a percentage point or less. You would not get 1 percentage point. So we can kind of do this. Another example is measurement error model. So we often have problems where we're regressing y on x, but x is measured with error. We can learn a lot by simulating some fake data, or we could actually just fit a measurement error model and stand. But either way, like, we can evaluate the hypothesis that we usually use, which is that we don't care about measurement error. Or omitted variable bias. It's a common thing that people will do. They'll say, what if there were some variable in there that we have to deal with? So again, like I feel that that there's a mismatch between what we do and what's in the textbooks. And because I don't quite have an answer, that's why I'm giving you this kind of disjointed talk. But let me just say that, like, our theories are there for a reason, but like, our theories are themselves only rough models of what we do. And so one example is adjudication and null hypothesis significance testing. So adjudication is a real thing, and it's my term for I have 2 models of the world and I want to choose one. Like, I'm not talking about decision making. I'm not saying like, I want to decide whether to do the innovation or not, whether to take the drug or not, whatever, whether to go or stop on the decision. I just mean more like we have different models of the world. So null hypothesis significance testing is a statistical mathematical procedure that kind of is supposed to do the adjudication process, but it's just such a crude model of things. And Bayesian hypothesis testing is also a crude model. And posterior predictive checking is great, but it's not about adjudicating between two models. It's something different, right? So I think that we have a tendency often to identify the statistical method with the goal. And I think that's wrong. And I've said this for a while, but what I only recently realized was that we have to think of these goals in the context of what we do, which is, as I said, when you're doing data science or statistics, I think you're acting like a little baby scientist. Like you're trying things out and you're trying to understand things. And I think we need to fit our theories around that. But between now and then, I just want you to try to use the methods you have available to you, but be aware that you are doing this sort of exploration. So I hope this will be helpful to you in the coming year.
Thank you very much. Excellent as always.
Thank you for the opportunity to talk with these people.
Of course, we love this.
Okay.
All right, folks, we are, believe it or not, back on schedule.